This is lesson 3.5, modeling with nonlinear regression. You're going to learn about using data to model data using exponential, logarithmic, and logistic functions, and linearize and analyze data. And of course, that's misspelled. All right, so an exponential regression. It's data that exhibits rapid growth or decay. And when you're looking at data that does that, you know that it's going to be an exponential regression. Sometimes it'll tell you that it is. Sometimes you have to look at it and tell. So our problem right here is that in Mesa, Arizona is one of the fastest growing cities in the U.S. And we want to use an exponential regression to model the Mesa population data. And then we're going to use the model to predict the estimated population in Mesa in 2020. So right here, this should say 2020. So we need to put all of this data into our calculator. So where you're going to go in your calculator to put this data in is you're going to go to Stat. And then you're going to go to number 1 and Edit. And your X goes in L1 and your Y goes in L2. So just to point out real fast that the data is slightly off. So this is 2000 right here, and all of this data should shift over one. Okay, now I'm going to show you what it looked like when I put it in the calculator. So what I've done in the L1 column, notice it's not the dates here, but it's the number of years since 1900. So I have a 0, a 10, 20, and on and on. And then this right here, this is the data in thousands. So I need to estimate, find an exponential regression. But before we find our regression equation, I need you to make sure that your diagnostics is turned on in your calculator. So what you need to do to check that is you need to go to second catalog, which is the 0. So second 0. And then hit the letter D, which is the x to the -1 button. And then just scroll down, and you'll have something called Diagnostics On. This is very important to us because we're going to be using this. So make sure it's on, hit enter, enter. When it says done on your home screen, your diagnostics have been turned on. And that's what we want. Now that our diagnostics are on, we need to run a linear regression. Or not a linear regression. This is not a linear regression. It said it was an exponential regression. So in your calculator, hit Stat again. You're going to go over to Calc. And then you're going to go down to exponential regression, which is 0. And you're going to run it. When that is run, I'm going to show you what you should have. Now these are the values that you should get. And this tells us a lot. Notice it's going to tell you what type of function regression equation that you ran. And so the equation is going to be 0.69 to a base of 1.067 to the x. This is our regression number. That's our correlation coefficient. And because this is really close to a 1, it was a good fit. If it's lower, like a 0.7 or something like that, it's a bad fit. And so if you want to actually then graph and look at the scatter plot and see how it all fits, this is what you're going to do. In order to see the data, you're going to hit y1 or y equals, and you're going to go up to plot 1 and hit enter. That turned it on. Now to see that what your data is, hit second y equals. And notice it should say that plot 1 is on. If you enter on it, plot 1, it should show you what type you have. Mine is the first box that looks like this, so it'll be points, and then my X list is L1, and my Y list L2, and then you can have marks. My marks are look like this. I'll show you what my page looks like. So that's what it looks like. Now, in order to graph all of that, you want your calculator to do it for you, because you can go in and mess with your window, but really you just want to hit zoom, and then you want to use number 9. It's a zoom stat. And it'll zoom to all of your data so that you can see it. And when I zoomed in, this is what it looked like. So that's all my data. Now, if I want the regression equation to be plotted on top of it, this is what I need to do. You need to go back to your y equals button. And then on Y1, when you're there, you're going to hit the vars button. And then go down to statistics. Then go over to the EQ button, and then select regression equation, which is number 1. And it will plot your line on it. Notice I've just changed it, and this is what my regression equation plotted over my data points looks like. So your calculator will do all of that for you. So you might want to make a note of where you want to go with all of these buttons to get this to do that. And the last thing we need to do here is to figure out what the population is going to be at 2020. So I'm going to use my calculator to do that as well, instead of plugging it into the equation, which I could do, but I'm going to go and hit second, and then calc, which is up under the Windows screen. It's the trace button. And then I'm going to go down to value, number 1. When I do that, it's going to ask me for my x. And so 2020, I'm not going to put that number in. I'm going to put 120 because it was 120 years after. So 120, when I put it in, it actually gave me an error. And the reason it gave me an error is because 120 is outside of this window. So I went into my my window feature, and then I changed my x to go to 120. So when I type in 120, it gives me an answer that it is 1,675, and that's 1,000, so it's 1.675 million is the population. So the next type of regression equation we're going to look at is logarithmic regression. And it's data that grows rapidly at first, and then it's going to slow down over time. So it's going to look something like this. A group of students studied a photograph for 30 seconds, beginning day 1. Beginning 1 day later, a test was given to each day to test their memory of the photograph. The average score for each day is shown in the table. Use the logarithmic regression to model the data, then use your data to predict the average score after 2 weeks. So we're going to go ahead and put the data in. We're going to get a regression equation, and then we're going to plug into that regression equation. So when I run the logarithmic regression, and that's going to be an LN regression, it's going to give me a logarithmic equation. It tells you the form. It's y equals a plus b ln of x. So my numbers are 73.109 plus b was negative 7.338 ln of x. So I go ahead and I graph all that in my calculator. I put in the equation, and I graph it. And now I'm going to show you what it comes out to look like. So this is what it looked like. I know you've done some regression equations in the past, so hopefully you remember. If not, just go through the steps, pick the correct one, and then we want to know what it's going to be after 2 weeks. So I'm not going to put in a 2. I'm going to have to put in a 14 because that's 2 weeks. But my window is not going to be right, so I need to go and change my x max to 14 because that's the data that I'm going to put in. And then I'm going to go ahead and calculate the value at 14. When I do that, I get 53.7. So my answer at 14 days, or 2 weeks, it is going to be a 53.74. So 53.7%. Here's a different kind of growth that you probably have not encountered yet. So it's logistic growth. And that's going to happen when it grows exponentially at first, and then it slows down and levels out, approaching a horizontal asymptote. And the reason this could be is like the spread of disease, because the disease spreads so far that then there's nobody else to spread to, so it has to slow down. Or like bacteria growing in a culture because its food that it eats on just runs out. So we're going to use this one now as well. And it's also in your calculator in that stat regression list. And it is down at number, or letter actually, so far down. It's that letter B under the stat list. Stat over to calc. So here we go. The number of TV ads for a certain product affect the percentage of people who purchase the product shown in the table below. Use logistic regression to find a function to model the data. Then use your model to predict the limit of the percentage of people who will purchase the product. So I'm going to go ahead and put this data into my calculator. Remember where you go? You go over to Stat, and then pick Edit, and you put it in L1 and L2. So when I do this one, I get the equation, and it's telling you what it looks like. So be aware of that. It says C over 1 plus A e to the negative bx. So you just plug in your numbers where they show up at. And so C was 55.86. And over 1 plus, it says A is a 50.24. E to the negative b, don't forget there's a negative right there. Look back up at the top to make sure, 0.064x. So that's the equation. And then I'm going to go ahead and use the same thing. I'm not going to plot this one this time, but I am going to clear out and put in the equation to graph it so that it'll run it for me, so I don't have to put it in there. Now, once I have this, it says to predict the limit. So we want to know the limit as x goes to positive infinity. Where is it going to level off at? So the limit as x goes to positive infinity. F of x goes to where? So when x gets really, really large. So I went ahead and graphed and extended my window out to, I think it was I went to 500. And I graphed it. And then I want to calculate what the value is going to be at 500. And it'll tell me that the y value is at 55.8 something. So we're going to round it to 56%. And we'll show you a little bit more in class how to get this, in case this isn't making any sense. But I'm going to show you also what I just graphed and looked like. So right, here's that graph, and I did in my calculator. And you notice I got it, and it looks like it's leveling off, and it did. And then I put the 500 in here, and it gave me back out my number. And here's the fun part. Sometimes you have to decide what type of model is best. You can do this by looking at the graph and or by examining the correlation coefficient of the regression. So let me show you what you might be looking at. So right here, this is a linear regression. And try to fit it to a line, but see this data? It's not looking so linear. And the regression right here is not very good. It's 0.74. That's bad. And then same data, if I try to fit it to quadratic, this is a 0.94. Notice that doesn't look like the data. A power regression, 0.94. An exponential regression, 0.99. That's really good. So that's the R that you're looking at each time. A logarithmic, 0.58. That's the worst one of all. And then a logistic, notice there's no R. It can't tell you because we don't know if it's going to level off or not. So there's no data there to say that it will. So just by visually inspecting, you can tell. You want to get the best fit possible. You can run the different regressions. Or once you run it, before you even look at it, you can just look at your regression. Sorry, not your regression. Your correlation coefficient, this R. When your diagnostics are on, now remember the diagnostics told you how to turn those on, so make sure they're on. And see which one's the best. So here's the data. Use the data to determine the regression equation that best relates the profit of website with the time it has been in business, and then determine the approximate time it will take for the website to earn a profit of $100,000 in 1 year. So I graphed it. What do you guys think it looks like? Was it a linear, a quadratic, a power, an exponential, logarithmic, or logistic? Think about that for a second. Now, if you're not quite sure, I'm thinking, okay, well, maybe it could be a power or maybe it's an exponential. I'm going to run both of those. I'm going to show you what the regression, the correlation coefficient is going to be. So when I ran the power regression, it came out to be 0.9676. That's okay. Not great, but it's close. Remember, the closer it is to 1 or -1, the better it is. And so then when I ran the exponential regression, though, it comes out to be 0.99999. This is the one we want. I want closer to 1. So I'm going to use that equation. And the equation is going to be a 999.9, a base of 1.78. 7 to the t. And of course you can have that put in your calculator, but we want to approximate the time it will take the website to earn about $100,000 in 1 year. So I want to set this equal to $100,000, and I need to solve that. So in order to solve it, I'm going to divide it by 999.9. Really, I guess we could have approximated that to about 100. So this is going to be 100. We'll approximate it to 0.178 to the t. Guys, how do you get rid of a base number? We can take the log of both sides. That takes the t, brings it out front. So this is going to be the natural log of 100 equals t, the natural log of 1.78. 0.78, not right there. Divided by the natural log of 1.78 to solve for t. And I get t is approximately 7.99 years. I'll tell you to do that. The last thing we're going to look at is linearizing. Okay, a correlation coefficient is a measure it's calculated, from a linear regression. Calculators linearize data, and that's transforming it so that it appears to cluster about a line. So they change the data to try to make it fit a line, and then they tell us how well it fits it. So how they do that is that if you tell that you want it to give it a regression equation of a quadratic function, it takes the data x, solves for y, and then it takes the square root of y, and it graphs that. An exponential function takes your x, solves for y, and then takes the natural log of y. With a logarithmic, it takes the natural log of the x that you put in, and then it gives you out a y. And then for a power function, it takes the natural log of x and the natural log of y. So I've graphed this data, the original data, and now I need to linearize the data using a power model. Right here. And remember, the power model said that we need to take the natural log of x and then the natural log of y. Those are n's, by the way. So I just need to take that data and take the natural log of each one of them. And when I do that, the natural log of x, I come out with negative 0.7, 0.4, 0.7, 0.9, 1.1, 1.3, 1.4. And then I'm going to take the natural log of y. And I get negative 0.97. At 0 I got 1.1. And then a 2.3, a 3.2. Literally just hitting your calculator, natural log of each of these numbers right here. And this is a 3.8, 4.4, 4.9, and then 5.3. So now I'm going to graph those. This is what I get when I linearize the data. So now I need to just do a regression equation on that. And because I linearized it, remember what kind of regression equation do you want to use? You're not going to use a power regression. You're going to use a linear regression. When I use a linear regression equation on that, I get from my equation y equals 2.97, so we'll just call it y equals 3x plus 1.1. Now this wasn't the original equation, so we're going to put this little hat over it to indicate that it was a linearized equation. And because x was equal to the ln x, we took the natural log of it, and y was the natural log of y, we're going to go back and replace that in here. So this is going to be the natural log of y equals 3, the natural log of x plus 1.1. What we want to do is we want to solve this for y. So what I need to do for each, I'm going to take each side to the base e because I want to get the y by itself, and it's already by itself. So these two cancel. I got y is equal to e 3, the natural log of x plus 1.1. So we need to break this apart the best we can. And what I want to get is y equals e3 ln x. Now if you add exponent, you can replace it and multiply it with the base. Coming back over here, where this 3 is right here in the front, we can take it up to the exponent. So this is going to be y equals, this is using your properties of exponents that we've learned about, x to the third, or properties of logs, and then e to the 1.1. Now right here, these two bases can cancel out. You get y equals x to the third and then e to the 1.1. Well, this right here is just a number. Put it in a calculator and we get that it is approximately 3. And so we get y equals 3x to the third. And there you go.